afternoon, everyone. Okay, so welcome to our sort of final tutorial. Okay, we still have one more revision classes after next week. Okay, so in terms of tutorial, this is the final one that covers all the recent topics that we have in class. Okay, yeah. So let me get started. Okay, and I will also talk a bit about the project first. Some things to take note of before we start the actual questions. Okay. Yeah. So in case there is some network issue or anything and I get disconnected, just stay in the call. Okay. I will reconnect again. Okay. So just in case. Okay, because my laptop is having issues once a while. Okay. So in terms of I will not go through all the theory material. Okay, because we have sort of covered that or you have sort of gone through that through the preparation for the studios. Okay, but I will just try to again summarize. So we have done the op amps. Okay, so you have operated in it in saturation mode, as an amplifier, okay, and also as a filter. Okay, so you can sort of see that op amp is actually very, very versatile. Okay, I'm not sure if you all have actually looked through the data sheet of the op amp. Okay, if you do go through the data sheet, you will notice that towards the later part, there will be always a section on called application notes. Okay, where they will actually give you a lot of example hardware connections. All right, to tell you how all the different ways you can use the op amp to be configured in different orientations and how it would work and so on. Okay, so of course online also you have a lot of resources, but generally op amps are very, very versatile. Okay, you can use them for a wide variety of applications. Okay, yeah. So spectral analysis is also another important area that you will see is very useful. Okay, yeah. So in a sense, just to share something. Many years ago, when I was like a freshman here in US, we did a lot of maths modules in the first year. All right, and I still remember doing all those this kind of equation solving, all the Fourier transform, cosine transform, Wavelet transform, and also a whole bunch of this math stuff that we did, and it was quite draining in a sense that you keep solving equations, but you don't understand why you're doing it and what is the application of it. All right, but that was of course when I was in year one, and then when I move on to I think in year 3 or what, then I did one module on image processing. Okay, and then we sort of learned how applying these kind of transforms on digital images actually plays a significant role in compressing signals. Okay, and reducing the amount of memory required. Okay, so that's why you're able to store digital files, okay, using much lower memory space compared to the raw data. Okay, so in a sense, in the past, we front loaded all the theory, okay, and then later on we sort of learned the application aspect of it. All right, but in EPP, I think we are doing a sort of a top-down approach, okay, where we give you the application, make you see its effect, all right, and then as you move on to higher years, you actually learn the theory behind it and the maths behind it. Okay, so I think it's a good thing, all right. That means at least for now, you can see the application of many of these things that you're currently using. Okay, and you'll see a lot more when you go to EPP2 as well. Okay, so you'll be exposed to a lot of, I'll say, a lot of technology, a lot of concepts, which is just at the surface level to make you appreciate what it can do and how we can make use of it. But the actual concepts and theories behind it are a lot more in depth, which you will learn in future modules. Okay, so that is sort of how EPP has been structured. Okay, so we also saw the application of the filter. Okay, and we will also look at some examples today. Okay, so again, I will skip all of this. Okay, because I think we have already gone through that and looking at that again in the questions. Okay, again, this sensor, like I mentioned, for the robot, okay, for your project, you need to have your IR sensor, your color sensor, as well as your ultrasonic sensor, all working very reliably. Okay, so if you have noticed, I don't know sure how many of you saw the sample robots that I will put on the table. Don't worry, every lab I will bring them out for you to have a look. Okay, so one of the things you will notice, okay, so I just want to go through some important points of the project before we go to questions. One of the things you'll notice is for the M board, you need to make sure you are very neat, okay, and compact sort of circuit, okay, and wiring. Okay, so if you look at the sample robots, you'll notice that the students have gone through great lengths to cut all the wires, make them very short, such that they sort of stick to the breadboard. They even use scotch tape or something else to secure the connections onto the breadboard and onto the M board and things like that. Okay, and all this is important, okay, because when your robot bangs into the wall, you never know what will get dislodged. Okay, and if in the midst of the competition, or I mean the assessment, a wire gets dislodged and you're trying to figure it out, your timer is still running. Okay, timer is still running. So it'll be a very highly tense situation, you know, when suddenly your robot bangs and a wire comes out, you do not know where to put that wire back in. Okay, so you need to make sure your circuits that you build are very, very solid, in a sense that they are neat, they are compact, and they are very tightly mounted to the M board. Okay, so this is very important. And of course, you need to make sure the M board, you bring the M board every week, okay, to the lab. Okay, so whoever is holding on to the M board, please make sure you come. If for some reason you are unwell, you can't make it to the lab, try to arrange another team member to pick it up from you earlier on. Okay, if not, the rest of your team members come to the lab and then they are sort of stuck, you know, they can't progress much without the M board with them. Okay, so always make sure that whoever is the M board takes some responsibility to make sure that it is brought to the lab. Okay, so another thing is, of course, throughout the project, while you are building up the robot, you will need you will want to try out different components and different circuits and so on. I think by now you all know the godfather of all CEG students is Uncle Janif. Okay, I think he has he's always a tremendous help to all students. Okay, and he is one who doesn't say no. Correct. Whatever you ask, he will just smile and say yes. Okay, and he will always be willing to help. Okay, but of course, having said that, please also make sure that whatever you borrow from him or from the lab, please return it. Okay, because he doesn't keep track. Okay, he doesn't, you know, you ask for a screwdriver, you ask for something, he will just give it to you. Okay, but always make sure that, you know, when you are done with it, before you leave, return back whatever you have borrowed from the lab, so that, you know, other students can also use those same equipment. All right. Another thing is timing. Our timing is 2 to 5. Okay, generally most of the time the labs are open by 1:30. Okay, those days where I am in the lab earlier, I will let you all know. Okay, so if let's say I'm in the lab by 12:30 or 1, I will just send out a announcement and then you can just drop by earlier if you want. Okay, but closing time is always 5, you know, so we have to stick with it. All right, another thing is, of course, do not enter other studios timing. Okay, so if you have, I mean, you have friends in other studios, other time slots, don't piggyback on them and try to go in and test your robot during their timing. Okay, because then students will start to complain. All right, you know, I'm using the maze, and you know, some other student is here using the maze, it's not supposed to be here, and so on. Okay, so I hope you understand. All right, so we stick to our timing. Same thing. Okay, if you notice students from other sessions coming to our lab, just let me know. Okay, I will ask them to leave, you know, so that it's fair to everybody that we use our own allocated time. All right, so those are just some of the points that I wanted to point out before we start the question. Okay, so the first question is on the power gain. Okay, so we are asked to show that if so we have an input, okay, and the output okay, or the amplifier. So the input is here, and we multiply input by a gain G. All right, and we are asked to show that if Rn equals to RL, then the power gain is given by this. Okay, so how do you go about looking at this? So we can say that the input side, okay, the power in is V in square over R in. Okay, and the output side, the P out is V out square over RL. Okay, so in terms of gain, okay, if you write the expression for gain in dB, you can say it will be 10 log, okay, to the base 10 of P out over P in. Okay, and that will be equivalent to 10 log to the base 10 of V out square over RL over V in square over RL. Okay, then if you simplify this expression, okay, what you'll get is 10 log to the base 10 of V out over V in square multiplied by, sorry, this is R in. This will be R in over RL. Okay, and by log rules, I can separate this out. So I can say 10 log to the base 10 of V out over V in square plus 10 log to the base 10 of R in over RL. Okay, and if R in equals to RL, then this component will be 0. Okay, so then left is this first component, and you bring the 2 down, you'll get 20 log to the base 10 V out over V in. Okay, so that is the way in which you can sort of prove this. Okay, so this is just to again confirm, sort of validate how we use this expression over here. Okay, when you calculate the power gain. All right, so that is the first question. Okay, so if anything, you can always again unmute and ask or put it in the chat. Okay, if there are no questions, I will just continue to proceed. Okay. Now this second question. Okay, so you'll notice that for op-amp, whenever you want to solve, there are two important steps. Okay, the first step is always we follow the op-amp golden rules. Okay, and in another thing to take note is in many cases we may also need to use the node analysis, okay, or KCL approach, okay, to define nodes and come up with expressions to solve for the unknown. Okay, so things that we learned before, okay, we need to apply them here as well. Okay, so in this question, all right, so the first step is always we apply the golden rule. So the one of the golden rules is V plus is equals to V minus, correct? So in this case, V1 is 0. Okay, so here is 0. That means here is also 0. All right, and if here is V0, this point is V0, then this point here is also V0. Okay, then what we can do is, we know that we want to get an expression to solve for V0. Okay, so whenever it is not a standard configuration, right? I mean, the standard ones are the inverting and non-inverting. So as long as it's not the standard one, okay, like in this case where you have some resistor network over here, okay, which is not so obvious to solve, then the technique is always to apply the node analysis. Okay, that means we define nodes, and from the nodes that we define, we come up with expressions and then solve for the unknown. Okay, so it's very similar to what we did before, okay, in the first half of the module. Okay, only thing is we are now applying the same technique to resistors connected to an op-amp. That's all. Okay, other than that, the principle remains the same. Okay, so what we can do is we can define this as a node, and we can say that as before, all the current go in or go out. Okay, so again, for a op amp, we know that there is no current flowing in or out of the input terminals. Okay, so there is no current flowing in this particular branch, okay, going to the negative. So for this particular node, okay, we can say that the expression, okay, could be V naught minus 0 over 2k plus, okay. So for this, I need to define a node over here. So I can call this VA. So I can say VA minus 0 over 4k equals to 0. Okay, then once I have that, I can simplify this to say VA is minus 2 V naught. So that is one expression. Okay, now I can come up with another expression. So maybe I can look at this point over here. Okay, if I look at this point over here, I can do the same thing. I can define all the current flowing into the node and sum it up as 0. Okay, so I can say that 9 minus VA over 4k plus V naught minus VA over 8k plus 0 minus VA over 4k equals to 0. Okay, so since I already have an expression that relates VA and V naught, I just take this and substitute inside here. Okay, and from there, once I solve everything, okay, so the rest is just solving the maths part of it, you will get V naught is negative 1.64 volt. Okay, so you can see that these are all the same techniques we used before. Okay, only thing is the nodes are now points in a op-amp circuit. That's the only difference. Okay, other than that, the same principle applies. Okay, so again, before we come to this stage, we apply the golden rules of the op-amp, which one of it is V plus is equals to V minus. Okay, so from there we can get some points and then we define some nodes and then we come up with the expressions to solve the unknown. All right, so I hope this is clear. Okay, so left is question 3. So in this question 3, we are asked to find an expression for V out. Okay, so the first thing is, again, we look at any of the inputs to see if it is a standard configuration. So over here, we can see that this is actually a inverting amplifier. This portion here is actually a inverting amplifier. Okay, so this point over here is actually negative 2V1. Okay, negative RF over R1. Okay, so I hope we can see that. Okay, the input is connected to the negative. We have a feedback resistor at R1 and the plus is connected to the ground. Okay, so this is the standard inverting amplifier configuration here. Okay, so the output of this first stage is a negative 2V1. All right, and then for the next stage, okay, we can see that you also have sort of a inverting amplifier also. All right, but in this case you have two inputs. Okay, so one is a negative 2V1 and the other one is a V2. All right, so to solve this, you can again use the op-amp golden rules. Okay, so since the plus is connected to ground, okay, plus is connected to ground, that means this is 0. So here is also 0. Okay, and with that you can define expressions. So I can say the current flowing here, here, and here all add up to 0. Okay, so the expression I will get is negative 2V1 minus 0 over 10k plus V2 minus 0 over 10k plus V out minus 0 over 20k equals to 0. Okay, so once you have that, then you have your final expression that V out equals to 4v1 minus 2v2. Okay, 4v1 minus 2v2. Okay, so this is actually in a sense, okay, though it's not covered in the syllabus, it is one of the configurations of the op-amp known as a summing amplifier. Okay, why do we say summing amplifier? Because if you look at it, it is actually two op-amp, two inputs connected to the same positive negative terminal here. So you notice that your feedback resistor is fixed at 20k. Okay, then I have one input which is negative 2v1, which is 10k. So the output of this will be negative of so the gain is 2, okay, a negative 2 multiplied by the input negative 2v1, which is 4v1. Okay, this is the inverting amplifier, correct? So for the first input, this is the output. Then I also have another input, which is 10k, and this input is v2. So for this second input, the gain is also minus 2. Okay, the gain is minus 2, but what is the input in this case? It is v2. So it is minus 2v2. Okay, so you can see that actually these are the two terms here, 4v1 and negative 2v2, which is here and here. Okay, so this is actually another sort of standard configuration, which is known as a summing amplifier. That means you can have multiple inputs, okay, connected together, okay, and the output will be a summation of each input multiplied by the gain. Okay, but again, like I said, this is not covered in the syllabus, so we can still solve it as before using our node analysis. Okay, so we still define the nodes, come up with the expression, and we still get the same answer. Okay, so again, don't worry too much about this. As long as you know this step over here, okay, then I think that is what is important. Okay, you applying the node analysis and then solving the expression. Okay, so that is our question 3 over here. Okay, question 4. Okay, so question 4 is a nice question. All right, so I always like to do this kind of design questions, all right, because it's sort of an application, correct, of a real world scenario. All right, so here you have a temperature sensing circuit using LM35, okay, op amps, resistors, LEDs, and so on. Okay, and you are given these specifications. All right, so one of the key things, okay, I mean, if you notice, for every studio that involves some hardware, we always give you the data sheet. All right, and of course, since you are still year 1 students, we extract all the important information from the data sheet and we give it to you in the studio handout. Okay, but as you go to higher levels, the expectation will change. Okay, we will just give you the data sheet and you have to figure out all these things by looking and reading at the data sheet. Okay, so you need to get comfortable, okay, that when you want to deal with some hardware interface, I must first get the data sheet. I must be able to extract out this kind of important information to understand how it behaves, how do I interface with it, how do I communicate with it, and so on. All right, so that is all important skills that you must develop along the way. All right, but for now, we just give it to you, all right, and we use it. Okay, so let's look at what we have. So we know that we have a LM35 sensor. Okay, and we know that it provides me with output such that at 25 degrees Celsius, it is 250 millivolt. Okay, and it varies by 10 millivolt per degree Celsius. Okay, so the system that we are building is, of course, just to differentiate based on a single point, which is 35 degrees. So it is fairly easy because I'm only looking out for a particular fixed temperature, which is 35 degrees. Okay, so since we know that it changes by 10 millivolts per degree Celsius, we can straight away say that at 35 degrees Celsius, it will be 350 millivolt. Okay, 350 millivolt. Okay, so design a temperature sensing circuit using LM35 op amps, resistor, LED. So we want to detect for 35 degrees Celsius. Okay, that means you want to detect for 350 millivolt. Now, 350 millivolt is a very, very small voltage. Okay, if I try to build a set, for example, a comparator, okay, in a sense, to detect 350 millivolt, to get accurately 350 millivolt is already a challenge, and on top of that, your signal is always susceptible to noise. Okay, if you use your scope and you sort of make the resolution of the voltage scale as small as possible, you'll notice that it's never a clean line, correct? There will always be noise. Okay, which means that it's very easy to get false triggers if I try to go to 350 millivolt. Okay, so one of the things we always do is we try to bring it to a range that is easier to deal with. Okay, so instead of dealing with 350 millivolt, if let's say I multiply by 10, okay, then I can say that I can deal with 3.5 volts. Okay, I can deal with 3.5 volts. Now, of course, you can say why 10? It could be 9, it could be 8. Yes, can. Okay, no problem. Okay, so what we are showing you is just one possible solution. Okay, so you don't have to say multiply by 10 and become 3.5. You can say I multiply by 9, multiply by 8. It's all up to you. Okay, so this is just an example. All right, if you are building this circuit on your own, you could have chosen any value as long as this final value that you come up with is something that is more easily attainable, all right, using some resistor or potential meter and so on. Okay, so let's stick with this idea first, that we are going to multiply it by 10. So the first stage is you want to multiply by 10. So to multiply by 10, okay, I can just pass it through a non-inverting amplifier. Okay, so again, all this is up to you. So if I say 9K and 1K, so it will be 1. So the total gain would be 1 plus 9 over 1, which will give me 10. Okay, so that means that when my input here is 350 millivolt corresponding to an input temperature of 35 degrees Celsius, okay, the output that I would see here would be 3.5 volt. Okay, the output that I see here will be 3.5 volt. Okay, so that's the first stage. Okay, so what we want to do now is we need to be able to compare this, okay, and trigger LEDs. Okay, so we already know from studio that the configuration is to use it as a comparator. So when I am above threshold, it goes to positive V set. When I'm below the threshold, it goes to negative V set or 0. Okay, so in that sense, I can directly say I need to connect this to 2 op amps. Okay, and how I'll connect is one op amp, I'll connect it to the negative terminal. Okay, and the other op amp, I'll connect it to the positive terminal. Okay, now I want to compare this against 3.5 volts. Okay, I want to compare this against 3.5 volts. That means my reference voltage should be 3.5 volts. How do I create 3.5 volts? Again, there is no fixed way to do it, correct? Up to you. Okay, so the easiest way is to say that I have 7 volts and then I take 2 resistors RR of equal value, then the center point would be 3.5 volts. Okay, so this will be 3.5 volt. Okay, so again, all these are just values that we just pick out to make our circuit easy to design. If you don't want 7 volts, you say I don't have 7 volts, I only got 10 volts. Okay, then you need to come up with another resistor divider to generate the 3.5 volt. Okay, so in our case, we just simplify it and say, okay, we have a 7 volt, we will just take two equal resistors and get 3.5 volt. Now, if I look at this first op amp over here, so I know that the negative is having a 3.5 volt. Now, if my input side here goes up, if from 35 degrees I go to 36 degrees Celsius, then this will be 360 millivolt. This will be 3.6 volt. Okay, so the 3.6 volt comes here, for example. Okay, so when the 3.6 volt comes here, that means the temperature is above 35 degrees. Then I want the red LED to be on. So I connect my red LED here. Okay, and it will switch on. All right. Now, if I look at the other end, where I say that it goes below 35 degrees, so let's say I go to 34 degrees, then it will be 340 millivolt, and that will be 3.4 volt. So now, if 3.4 volt comes here, okay, if 3.4 volt comes here, what happens? The positive is smaller than the negative, so the output in our case, so in this configuration, we will use a single supply. So this will be plus VCC, and this will be ground. Same thing over here, plus VCC, and this will be ground. So when the positive is smaller than negative, you'll go to the negative supply. In this case, is ground. So ground means the LED will not light up. Okay, but in this situation where temperature is below, then I want the green LED to light up. So that's where the other op amp comes in. Okay, so what I need to do is I need to make sure that this reference voltage is also connected to the positive of the op amp. So in this situation where my input temperature is 34 degrees, and after the amplification I get 3.4 volt, and here is 3.5 volt, then we can say that the temperature that we are reading is below 3.5 volt, which will then trigger the first op amp. So then I make the green LED light up. Okay, so that is how we can sort of go about designing this whole circuit to fulfill this criteria. Okay, like I said, a lot of these things are just design decisions. Some of them, okay, you are free to be flexible, correct? Like this doesn't have to be 10, it can be any value. Then whatever value you get, then this reference will have to correspond to that value. All right, and whatever supply you have here, whatever resistors are all again design choices. Okay, so this is one approach. Okay, using two separate op amps with a single supply. Okay, now you can also sort of improve this design. Okay, you can also improve this design with a single op amp. Okay, a single op amp. Yeah, how will I do that? So if let's say I want to design the same thing but only use a single op amp, all right, what I will do is this. Okay, so I will just draw the op amp first. Okay, and I know that my negative is connected to a supply, to a reference point here. So this is 7 volts, and this is R and R. So here is my 3.5 volt. Okay, and this voltage here is the voltage of the LM35. Okay, so I'll call this here VM LM35. That means the voltage after I amplify by 10. Okay, so as before, if let's say this voltage is, let's say 3.6 volt, then I want the red LED to light up because it is bigger than the reference. So to make the red LED light up, okay, I'll connect it this way. Okay. Now, in order for this single op-amp solution to work, one of the things is we must have a dual supply. So this will be plus VCC and this will be negative VCC. Okay. So when my V plus is greater than V minus, I will go to plus VCC, which will on the red LED. Okay, it will on the red LED. Now, in the other situation where my input is smaller than 3.5, so let's say it's 3.4 volt, then it will go to negative VCC, negative VSET, correct? So in order for me to switch on the green LED in negative VSET, what I need to do is I connect my LED this way. Okay, so what happens when my output goes to negative VCC, then 0 is higher than negative VCC, which will allow the current to flow here in this direction and switch on the LED. Okay, when it is positive, okay, when you go to plus VCC, current will flow in the direction of the forward bias LED here and light up the red LED. Okay, so that is how you can sort of combine, okay, these two op amps, okay, into a single op amp solution. Okay, so okay, let's go on to the next question. Okay, so the next question, so the next few questions are all quite similar and related. It's all about filter design. Okay, so what we have is we are given that we have an audio clip in the range of 100 to 3000 hertz corrupted with 10 kilohertz noise. Okay, and the signal is also very soft. Okay, what we want is to have a active low pass filter with pass band gain of 6 dB. Okay, suppress the 10 kilohertz noise by 20 dB relative to the pass band gain. All right, so what does that mean? So if I were to draw the response that I want, okay, or the frequency of the system, so we know that around 100 to 300 hertz, 3000 hertz is the signal that we want. We also know that at 10 kilohertz there is a spike, okay, a noise spike. Okay, so what we want is we want the gain, okay, in the pass band to be 6 dB. So here should be 6 dB. Okay, and the noise should be suppressed by 20 dB relative to the pass band. That means when I create my filter and I go, okay, so this distance here, okay, this distance here from here to here should be minus 20 dB, okay, relative to the pass band. Okay, so that is what we want. We want the 10 kilohertz noise to be suppressed by 20 dB relative to the pass band. Okay, and at the same time, the gain of the pass band is 6 dB over here. Okay, so how do we go about this? Okay, so the first step is the design of the filter. Okay, so we know that a filter, in this case, an active low pass filter, has two parts. One is the actual filter part. So the filter part is nothing more than just your RC. So this is your B in, you have a resistor and capacitor. Okay, so this is actually your filter part. Okay, this is your low pass filter. And the active element is the one that is providing me with the gain. Okay, so I can put the RF here and R1 here and the ground here. Okay, so we can say that this point here is your V plus and this is your V out. Okay, and what we want is that 20 log to the base 10 of V out over V plus must be equals to 6 dB. Okay, then if you try to solve this, V out over V plus will be 0.3. Okay, and then that will give me a ratio of V out over V plus to be equals to 2. Okay, so the gain of V out over V plus will be equals to 2, which means that this part over here, okay, which is 1 plus RF over R1 will be equals to 2. Okay, so that is the first part, the active element of the filter. Okay, now the next thing is, let's look at the relationship between V out and V in. Okay, the relationship between V out and V in. So we know that V out over V in is equals to V out over V plus and V plus over V in. So there's two parts to it. Okay, the V out over V plus is the gain of the non-inverting amplifier. Okay, and that one is already known to us as 2. Okay, V plus over V in is the voltage at the capacitor with respect to the resistor and capacitor. So this is nothing more than a voltage divider rule. Okay, a voltage divider rule, which is XC over R plus XC. Okay, so you put in all the expression, 1 over j omega c R plus 1 over j omega c. So that will give me 2 over 1 plus j omega RC. Okay, so that is the relationship between the output and the input. Okay, the relationship between the output and input. Okay, in the standard expression here. Okay, and what we want is, we are interested in the log. Okay, because we're interested in the dB. So what we want is the power, okay, should be dropped by 20 dB relative to the pass band gain. So I need to do the amplitude first. All right, so this is V out over V in, and I'm going to look at the amplitude of it. So that will be 2 1 square plus omega RC square root. Okay, now if I take the log, okay, if I take the log of it, then what will I get? I'll get 20 log to the 2 minus 20 log to the 1 square plus omega RC square. Okay, so this is an important step from here to here. All right, you notice that all the questions you're going to do it the same way. All right, so when you look at this expression, you will notice the two components. Okay, so what are the two components? This first component is your pass band gain. Okay, why is it the pass band gain? Because you notice that there is no omega component here, there is no frequency component here. That means this is the gain that you will get at all frequencies, correct? Because there is no omega in this first term over here. All right, and that is what you want here. When you first start off, you want the gain, okay, of a particular value, which is 6 dB. All right, and you want that particular gain to drop, okay, as the frequency changes, and that is this component. Okay, so this is actually the stop band. Okay, why? Because this is the gain that you will reduce by depending on the omega value. Okay, depending on the omega value. Okay, so the expression has two parts. Okay, the first part is the pass band, which is independent of frequency, and the second part is the stop band, which is dependent on the frequency. Okay, so now the first thing is, we know that this second half is the stop band expression. Okay, the second band expression. Now the next thing is, we want to, or we have a condition to fulfill. And what is the condition? The condition is that the noise must be suppressed by 20 dB relative to the pass band. Okay, so at 10 kilohertz, I must have dropped by 20 dB. So the condition is clear. The condition is at 10 kilohertz, this component must be equals to 20 dB. Okay, or in a sense, negative 20 dB. All right, so we are going to be focusing on this second half of the expression. Okay, the second half of the expression. So we're going to say that minus 20 log 1 plus omega RC square is equals to negative 20 at f equals to 10 kilohertz. Okay, this is the requirement that we have to fulfill. Okay, so once we get this, then the rest is solving the maths part. So 1 plus omega RC square equals to 10. Okay, then from there you can get RC value to be 10 square minus 1, 2, 5, 10K. All right, and that will give me a value of 1.584 times 10 to the power of minus 4 seconds. Okay, so we know that as long as my RC is giving me this value, then when I work backwards, I will fulfill this criteria that at 10 kilohertz, I will have a reduction of 20 dB. Okay, so for RC to be this, you can just take any combination of R and C. Okay, any combination of R and C, they will give me this value over here. Okay, now of course, in most cases, what we will do is we will fix the C and calculate R. Okay, why fix the C? Because when you get any funny value of R, it's easy to use a potentiometer and get that particular R value that you want. Okay, but for capacitance, a variable capacitor is quite expensive. Okay, so it's a lot more easier and cheaper to fix a C value with a standard capacitor and then use a variable resistor to get whatever resistance that you want. Okay, so in this question, you are not given any particular R or C value to work with. So you can sort of say that I choose any RC value to get what I want. Okay, now, so the first thing is we know that this condition has been fulfilled, okay, with this design. Now, the next thing is, what is my cutoff frequency? Okay, the next part of the question is, what is my cutoff frequency? So what is the cutoff frequency? The cutoff frequency is, I need to drop by 3 dB. Okay, so when here to here is minus 3 dB, the point where it touch and come here, that is the FC. Okay, that is the cutoff frequency. Okay, so how do I now know what is the cutoff frequency for this particular filter that I've designed? Okay, so we are going to come back to the same approach. Okay, so the approach is the same. That means we're going to say that we know that the first half is the pass band, the second half is the stop band, which is dependent on frequency. So for this second component right now, we can say that minus 20 log to the base 10 of 1 square plus omega RC square must be equals to minus 3 when F is equals to FC. Okay, when F is equals to FC, then we know that the reduction is minus 3 dB. Okay, so it's the same expression, but now we are working with a different F. All right, so if I work backwards now, I can say that 1 square plus omega RC square will be equals to 10 to the power of 3 over 20, which will be root 2. Okay, so since we know that we already have on the left hand side 1 plus another component, so this component must be equals to 1. Then you will get root 2. Okay, so we can say that omega RC must be equals to 1, which is 2 pi f RC equals to 1. Okay, so with that we can find f, in this case this is FC equals to 1 over 2 pi RC. Okay, which is actually the same formula that we saw in our studio handout. All right, and since we know that RC value is this, we can straight away substitute 2 pi, this value over here, 1.584 times 10 to the power minus 4, and you will get an answer of 1 kilohertz. Okay, so if I go back to my waveform here, you will see that my FC is actually before or comes before the frequency that I actually want. So this is 1 kilohertz, but the audio clip is up to 3000 hertz. Okay, so this is part and parcel of how a filter works. Correct? When you create a filter, okay, it is never a case where you just directly cut off an MC. Okay, theoretically, yeah, you may think like that, but in reality, there is a slope. Okay, which means that, okay, you need to compromise. All right, that if I design it this way, my signal that I want, which is audio clip, also get attenuated. All right, of course, you don't have to live with this. Correct, you can come up with a better solution. Okay, and what is a better solution? Okay, the better solution is to use what we call a better filter. Okay, so let me come here. So a better filter means, okay, what we created is what we call a first order filter. Okay, a single RC. Okay, you can cascade, okay, a few different first order filters and come up with what we call a second order or third order filter. Okay, and when we create higher order filters, what happens is the roll off is faster. Okay, so if you come back to this, okay, the reason why we are going to be losing the 3000 is because my slope for first order filter is negative 20 dB per decade. Now, if I can roll off faster, that means if I can roll off faster, that means from my FC, I can roll off faster. Okay, then maybe I can push my FC a bit further off. I mean, instead of 1K, I can push it to maybe 2K, 2.5K, and try to roll off faster. Then I can still eliminate the noise and still keep my signal. All right, so in a sense, we can play around and use high order filters. Okay, and if I use high order filters, then my FC can be pushed further off, closer to the end of the pass band that I want. Okay, again, it is a trade-off, because then when you talk about high order filters, then your filter circuitry becomes more complex. Okay, it becomes more complex. So it's just a trade-off between what you're willing to sacrifice and what you want to get in the end. Okay, so in this case, this design, we achieve the objective, okay, which is to reduce the noise. Okay, but again, the trade-off is our cutoff frequency is a bit earlier on. All right, and which means some of the audio signal also gets attenuated. Okay, so that is how we do this. Again, this is, I would say, a very important step for you to remember. All right, that almost all our questions we will have the same approach. Okay, to figure out how to evaluate the dB or relate the dB to a particular frequency. Okay, so these are all the steps. Okay, so I'll not go through all of those steps since we already done it here. Okay, question 6 is to design a passive low pass filter to suppress 12 kilohertz noise by at least 20 dB. Okay, so it is actually the same thing. The same thing. The filter design for low pass filter is the same as before. Okay, so if you start off with the same idea that V out and V in, okay, is equals to XC over R plus XC. Okay, then when you take the log, okay, take the magnitude and we take the log, you'll get the same thing. All right, that means V out over V in, okay, in dB will be equals to 20. Okay, okay, so before dB, maybe I just put the expression. It should be 1 over square root 1 plus omega RC squared. Okay, so in dB it will be 20 log to the base 10, 1 minus 20 log to the base 10, 1 plus omega RC squared. Okay, so again, because this is a passive filter, right, there is no additional amplification in the passband. Okay, it is as it is. Then you make a reduction based on the omega value here. So what we want is, for this portion here, we want it to be minus 15 dB at 12 kilohertz. All right, so that is the same technique as before. So minus 20 log to the base 10 of 1 plus omega RC square equals to minus 15, okay, at F is equals to 12K. All right, then the rest, once you come to this stage, then the rest is all the maths only. Okay, 10 to the power of 20. Then you solve for RC, you get 73.4 microseconds. Okay, so that is your RC value. Again, after that, you can choose, okay, whatever values that you want. Okay, I think in the handout, what they have given is, if I choose C as 10, in nanofarad, then R will be 7.34K. All right, so again, this is just any values, all right, just to get whatever that you want. Okay, so this question is similar to the earlier question. Okay, so let's look at the other type, which is the high pass filter, and show that the cutoff frequency is actually the same formula, right? Just now for low pass filter, we say the cutoff frequency is 1 over 2 pi RC. And now we're going to show that the high pass filter also has the same cutoff frequency. Okay, so how do we do this? So if we come up with the same expression, so V out over V in is R over R plus XC. So XC is 1 over J omega C. Okay. Now, if I multiply both the numerator and denominator by 1 by R and 1 by R, then what I will get is 1 over 1 plus 1 over J omega C. All right. Now, in terms of the magnitude, okay, so what you will get is 1 over 1 square plus 1 over omega C square, sorry, omega RC, is RC over here, square. Okay, square root. Okay, now rightfully, when you look at it from the magnitude, and when you do complex numbers, we know there is always a magnitude and a phase. All right, we have done that in the complex number part. So actually, there is a phase element here. So there is a phase element here, and there's a theta over here. Okay, only thing is in our EPP1, module, we are not concerned about the phase. All right, we are just focused on the amplitude. Okay, but there is also a phase, okay, element that sort of has an effect on how the filter signal will look like. Okay, but that is not part of the module. All right, so that one is probably something you will learn in another module in the future. All right, so for now we are going to focus only on the amplitude part. So for this amplitude part over here, when I do the log, okay, what I'll get is 20 log 1 minus 20 log to the base 10 of this whole term here, 1 plus 1 over omega RC square root. Okay, and as before, for a cutoff frequency, okay, to get the cutoff frequency, we know that this must be equals to minus 3 dB at f is equals to fc. All right, so the same approach we're going to take. So minus 20 log to the base 10 of 1 plus 1 over omega RC square is equals to minus 3. Okay, f equals to fc. Okay, then 1 over omega RC square is equals to 10 to the power of 3 over 20, which is equals to square root 2. Okay, so as before, we will see that this element has to be equals to 1. Okay, for this to be equals to 2. So omega RC is still equals to 1. All right, and that will imply that FH will be equals to 1 over 2 pi RC, same as before. Okay, so that's how we actually come up with the same expression for both the high pass and low pass. Okay, yeah, so there's one more question on the same technique. Okay, so we have a frequency humming from the aeroplane from 30 to 60 hertz, and we want to hear music which is 800 to 3000 hertz, and we want to have a high pass filter to suppress the humming by at least 21 dB. Okay, so if I were to draw the response, okay, we can say that 800 to 3000 is what I want, okay, which is the response would be around the passband here, and the noise is from 30 to 60. Okay, so somewhere here 30 to 60 is the noise. All right, so what I want is I want to make sure that whatever gain I'm getting here, it has to drop by at least 21 dB. Okay, at the point of the noise. That means when I draw my graph here, it should be something like this, where the point where the cutoff that aligns to 60 hertz is 21 dB lower than the passband gain. Okay, so this is the key thing here. This and this must be aligned. All right, so that is the objective. Okay, that is what I want to fulfill. All right, and since this is a high pass filter, okay, we know the expression from the earlier question, so I can straight away put in my expression here. Like I say, V out over V in. Okay, so your final test will also be MCQ. Okay, so you don't need to worry about the derivation as long as you know which expression to use. All right, then you can straight away use it. Okay, so in this case, the high pass filter will be this 20 log to the base 1 minus 20 log to the base 10, 1 plus 1 over omega RC square, and the same thinking applies. So what we want is this should be minus 21 dB at 60 hertz. All right, so we're going to just focus on that, minus 20 log to the base 10, 1 plus 1 over omega RC square, equals to minus 21 at f equals to 60. Okay, and once you have this, then the rest is as before, just the maths. Okay, 10 to the power of 21 over 20. So after you solve everything, 1 over RC is about 11.176. So in this case, 1 over 2 pi f, 2 pi f. So this is 60, and RC will be equals to 11.176. Okay, so if I bring the 60 over, so I get 1 over 2 pi RC will be equals to 60 times 11.176 will give me 670.5, and that is actually your FC. Okay, so since we know that the expression for the cutoff is 1 over 2 pi RC, all right, so once we get that expression 1 over 2 pi RC, we know the cutoff frequency that we need, okay, for this particular filter here. Okay, so that is basically the filter that you need to design. A filter with a cutoff, a high pass filter with a cutoff frequency of 670.5. So if I come back here and I draw it, that means the cutoff frequency here, okay, for minus 3 dB over here will be equals to 670.5. Okay, so with that cutoff, I can be assured that at 60 hertz, the noise, okay, or the signal would have been suppressed by at least 21 dB. Okay, so if you notice, it's all the same, correct? The technique is the same. The expressions are the same. Only the numbers change. So as long as you know high pass, I use what expression, low pass, I use what expression. Okay, then you are good to go. All right. The only thing here to note is for a low pass. Okay, if I go back here, just to show you the difference. When I doing creating a filter for low pass, okay, I am focused on how the signal is going to cut off at the lower end or the higher end of the frequency. Okay, so it's 100 to 3000 hertz. Okay, I look at how the cutoff might affect the signal that is what I want in the passband gain. Okay, in design of the high pass filter, okay, the frequency we need to be aware of that you want to suppress is actually the high end frequency. Okay, so even though we want to suppress 30 to 60, okay, we need to make sure that at 60 hertz we are able to suppress it. Okay, so next is question 9. Okay, last two questions. Okay, so the last two questions are again design questions on interfacing with sensors and so on. Okay, so what we have is we have a pressure sensor, 250. The expression is this. So again, like I said before, these are important information that we need to extract from the data sheet, okay, of the system, okay, of the peripheral sensor that we buy. Okay, so since we know that the pressure sensor is having this expression, okay, and in our particular setup, we are only dealing with 10 psi as a maximum. Okay, so we want to capture this signal, okay, and we want to make use of the Arduino's ADC input range, okay, for conversion to a digital value that we can then use later on. All right, now if you are given a project like this, okay, in real world, all right, whether it's a pressure sensor or temperature sensor or anything, the first thing I would say is I don't want to use this sensor. Okay, why? Because why do I want to go through the hassle of dealing with the analog signal and then trying to do A to D conversion and so on? I would rather try to look for a sensor that straight away gives me a digital signal. Okay, then I just interface digitally and I get the value immediately. All right. Again, that would be my ideal solution. Okay, to avoid all this hassle. Okay, but if you have no choice, okay, for some reason, okay, then you have to only use analog version, then you have to go through this process. Okay, so the first thing is we want to understand the range. Okay, so we know that maximum pressure is 10. So if I'm having 10 psi, okay, then what does it translate to? Okay, in terms of the values we are put inside this expression, so we can say that 10 is equals to 250 over 250. Okay, V out over VCC, which is 5 multiplied by subtract 25. So I'll get V out is equals to 0.7 volts. Okay, so that is the highest pressure that I expect to read in my setup. How about the lowest pressure? So let's say is 0 psi. Okay, so with 0 equals to 250. Okay, V out over 5 minus 25. Okay, then you get a V out of 0.5 volt. Okay, for 0 psi. Now imagine that I take this sensor. Okay, I take this sensor where the range is 0 psi to 10 psi. Okay, and the output range is given, okay, without anything is 0.5 volt to 0.7 volt, and I try to connect it to my ADC. What would happen? Okay, if you remember, okay, our ADC is a 10-bit ADC, which means that our range, okay, the input range is 0 volt to 5 volt, and this 0 volt to 5 volt is mapped, okay, to a scale of 0 to 1023. Okay, which means that if my input is all squeezed to only a 0.2 volt range, when I map it over, it will be values that are almost close to each other. Okay, which is firstly prone to a lot of error. Okay, because when you amplify, you only get a few values to differentiate 10 different psi values. Okay, and anything in between as well. Okay, so it is highly inaccurate and you do not get any clear resolution. So it means if you get something like 1.2, 1.3, 1.4, 1.5, they may all show the same ADC value. Okay, because it can't differentiate at such a small scale. All right, so you do not want to do this. All right, you do not want to take this direct PSI translated voltage and put it into ADC. Okay, even though you get some value, you can't really make good use of the value. Okay, and you won't really benefit from in trying to read all the values from 0 to 10. So what we want is we want to expand this range as much as we can, okay, to sort of maximize the ADC that we have. So to maximize the ADC that we have, we need to go back to maximizing this. Okay, how do I take this small range and expand it? Okay, so what we want is we want to take this 0.5 to 0.7 and pass it through something else before I go to the ADC. Okay, and since the ADC is expecting a value of 5 volt maximum, what I can do is I can choose to maximize my maximum value, which is 0.7 to 5. Okay, so if I take 5 divided by 0.7, I will get, okay, a gain of 7.14. Okay, so 7.14 gain, okay, which means that the 0 volt, so 0.7 volt at the input side would be expanded all the way to 5 volt at the input side. All right, of course it is still not ideal, as in a sense that here you will have 0.5 volt, correct? So even though the top range goes to 5 volt, okay, the bottom range goes to around 3.5, 3.6, okay, around 3.5 or 3.6 there. Okay, so even though it is still not the most ideal, okay, let me just check that. Okay, so even though it is not the most ideal, you get a much bigger range than originally. So originally you had a range of only okay, 0.2. Okay, now you have a range of around 1.4. Okay, so 7 times greater, okay, than what you originally had. So this is again part of what we call signal conditioning. That means when we deal with a sensor or a peripheral, okay, sometimes we can't take the original signal as it is. We may want to perform some signal conditioning, some processing to make it more suitable with what we are doing in the next stage. Okay, in this case, it's the ADC. Okay, so of course, at 7.14, you can easily get it using a non-inverting amplifier configuration. Okay, so here, if I take non-inverting, then I can take RF over RI at 6.14. Okay, so again, these are just an example, correct, of how you can get this done. Okay, so now the last question here. So the last question, we have a humidity sensor where the VR changes by 30.68 millivolt per relative humidity percentage. So at 0%, you get this value. Okay, and we want to design a humidity sensing circuit using the sensor, op-amp, and Arduino Uno. So the same thing we need to first understand. So we know that at 0%, we get 0.958 volt. Okay, now at 100%, what do we get? So I put it into the range that we had. So it will be the 0.958, which is at 0%, plus this relationship, which is 30.68 milli multiplied by 100. Okay, because now it is 100%. So that will give me a value of 4.026 volt. Okay, so this is not so bad. This is not so bad because and now my range is 0.958. Okay, all the way to 4.026 volt. Okay, so the range is actually quite good. Okay, but of course, if you want to expand it a bit more, you can try to make this go all the way to 5 volt. Okay, so to the gain that I need will be 5 over 4.026, which will be 1.242. Okay, so that will allow my input signal to stretch all the way to 5. Okay, and the lower end also will stretch a bit. Okay, but the overall range will be higher than what you originally had. Okay, so the key thing is from this last two questions is very simple. Whenever I want to use the ADC, okay, we want to maximize the input to make full use of the range that we can support. So if I can support 0 to 5 volt, I want to make full use of this so that the values that I get are spread out across the full output range. Okay, and the more spread out they are, means that the more accurately you can work backwards to know the actual analog value. Okay, if you are squeezed, okay, all the values are squeezed to a small range, then you can't really differentiate a lot of the input signals. Okay, for many of the signals, you may get the same ADC value. All right, so that is what we want to achieve before we do ADC operation. Okay, so that sort of brings us to the end of the questions that we have. Yeah, anything that anybody wants to ask about the questions or the project? Anything? Okay, so again, the project, the specs are all out. Okay, there's a document there. Okay, the amazing race document. Please go through that document very well. Okay, and towards the end, there are a lot of resources that are already given. Okay, those resources are very useful, especially for the programming part. They tell you exactly how to use the library functions to interface with the sensors, to control the motors, everything. Okay, so please make sure you read the document in detail and understand how to interface the sensors physically, as well as using the library functions to go back, so use library functions to control all the peripherals that you have. Okay, so please do that. Okay, so question 5. Okay, so yeah, if you have any questions, you can stay back and ask me. If not, I will suggest, I mean, that's all we have. And next week on, do make use of the time wisely. You only have the lab slot, to focus on. So make full use of the time. Okay, whatever you can prepare ahead of time, at home, your code, whatever you can test, please do that. So when you come to the lab, you make full use of the maze to do the testing. All right. If you come to the lab and then you start building the writing the software and trying to think of the circuit, then you waste a lot of time. Okay. You can always drop by the DSA lab to take stuff. Okay, that one is not an issue. Okay, so if you want to take resistors, capacitors, whatever that you need, you can always drop by the lab and take it. Okay, you can also work outside the lab. Okay, outside the lab usually there's a table there. Okay, if you want, you can take some components and you can build your circuit and work on it outside. All right, if you want to test something. All right. Okay, whenever I'm in the lab earlier, I'll let you all know, so you can also come in and start your work earlier. Okay, so that's all I have. I will still stay on the call if there's any questions. If not, thank you, and I will see you all next week. Yeah, I will upload. Yeah, I'll send you all this document. Okay, together with the recording later.
Sorry, Bob.
Yeah.
For this question, right, question 5.
Yeah.
Like, so there is an input signal range of like 800 to 3000, right?
Yeah.
Like, do we have to use that in our? We don't actually need to use that, right?
Yeah. In
100 to 3000.
this case, we are not using that to design the filter. So in our case, our criteria is in the filter design is more of suppressing the noise, and we also try to explore the side effect of the filter in the sense that it also sort of suppresses a bit of the audio signal that we want. Yeah, so in this case, yeah, we are not really making use of the 100 to 3000 in the design of the filter.
Okay, thank you. And when they say like we need to design an active filter with a passband gain of 6 dB, right? That 6 dB is V, because like here you use like V plus relative to V out. Like I thought we have to use like V in relative to V out.
So again, V?
Like because like you use 20 log base 10 V out over V plus, right?
Yeah.
Equals to 6. I thought we have to use like V out, V in. No.
So because this is the gain with respect to the filtered signal, correct?
Filtered signal, like so not the input signal.
Yeah. So the filtered, so after pass through the filter, the signal is V plus, correct? So that's why we use V plus over here.
Okay, thank you.
Okay, so anybody have any other questions? Okay, so I think I'll end the call. If there's anything, no issues, we can still discuss. Okay, any questions during the class. Okay, so thank you. I'll see you all on Tuesday. Okay, bye.